continue from the previous segment by maybe simplifying a little bit the transmission coefficient. We'd actually found it in kind of a obscure form. I'd written it like this. G is defined to be this mess, and then I have these expressions here, and then this sine squared of k prime w. So I had the scattering transmission coefficient. And let's first take a look at G. Actually, it simplifies pretty nicely. Um, I can, if you look at that, you can write this as the difference of k plus k prime squared minus k prime squared, and that whole quantity squared. Square this, you get this term. Square this, you get this term. And then the cross terms, I'll get two of those and they'll both be minus signs. So G can be written in this form. And then I go ahead and expand these out. The square of k plus k prime and the square of k minus k prime. And they've got some cancellation. A k squared here will cancel this one. A k squared here will cancel this one. A k prime squared here will cancel this one. And so I get 2k k prime minus a minus 2k k prime inside the brackets, and that's just 4k k prime, and then I square that, so I get 16 k squared k prime squared. So substantially simpler. And so go ahead and plug that in for G. So 16k squared here, k prime squared, and that gives me this expression. K prime k squared, that was my G, and then the rest of the term was I can write as well. I notice that this one I can write k prime times k minus k prime is going to be k squared minus k prime squared. But I've got two of those, and so I can square to each of these, and so I can write both of them as that difference in k squared and k prime squared. And since I've got two of them, they multiply together gives me k squared. So that's this reduction of this product here. Oops, no, the reduction of this product here. Sorry about that. This product here to just be 4 times k squared minus k prime squared, all quantity squared with the sine squared term. And this is nice because I've got some cancellation. This first term, really my G term, is exactly what was in the denominator here. So this into this will give me 1, and this into this. Oh, there's several ways you can write it. You can just write it as this quantity squared here divided by the 16, but one of the 4's here will cancel with one of the 4's in the 16 to get k squared and k prime squared on the bottom. Or write it as a combined. I think this term is maybe a little bit easier. And now then we need to put what all that stuff is in. The numerator here, k squared minus k prime squared, well, that turns out to be pretty easy because remember k is the square root of 2me over h bar squared, and k prime is 2m times e plus v naught over h bar squared. And when I square those, I just get 2me h bar squared and 2me plus v naught over h bar squared for these two terms respectively. The e terms will go out, they're identical, and so I pick up a minus. This simply becomes minus m v naught over h bar squared for the numerator here in this piece. The denominator is a little bit different, not much more difficult. K times k prime squared, well again, k we know is the square root of 2m e over h bar squared, and k prime is just this factor squared. And so these become the product of these two. And so I plug both of these back up here, both of those. And when I do that, I get this. this piece here was the k squared minus k prime squared. Squared. So there's k minus k prime squared. And then the k prime, that is just this, and that was in the k squared k prime squared. A 4 k prime squared is these. And again, we get a fair amount of cancellations. The h bars go out. H bar squared terms go out. I get I get 4s that go out. I get an m squareds that will cancel. And on top, I'm left with v naught squared, and on bottom, I've got 4e times e plus v naught. All that times sine. K prime, we can again substitute here for that. And then often, a term that you often see, and we'll look at this a little later, but it's convenient to factor out an e out of this, and so when I do that, I've got an e squared here and a 1 minus v naught over v, and then the e I combine with the 1 on top. And the thing that's nice about this is it shows that v naught and energy e are both energy units, and so this is dimensionless, this whole coefficient, as is everything really in here. Yeah. And again, remember W is twice the well radius. W is the diameter or the width of the well. And that's really 1 over t, so let's look at the transmission coefficient. I just have to take the reciprocal of this relationship above. If you like, you can get the reflection coefficient. Remember, the reflection coefficient plus the transmission coefficient always have to add up to be 1. And so I don't have to go through a long involved calculation to get r. But I can use this relationship to get r in terms of t, since I have t. And when you do that and simplify a little, I get this rather complicated looking expression. And now then we can look at some limits. In particular, I want to look at the limit where v naught goes to 0. And if you look, as v naught goes to 0, then the top vanishes, and so r goes to 0. And likewise, the transmission coefficient is as v naught goes to 0, this term vanishes here, and so this whole term vanishes, and so the transmission coefficient just goes to 1. So it reduces to what you would think. If there's no scattering potential there, there shouldn't be anything reflected, and all the initial wave just goes straight through. Well, you'll sometimes see these in this form. We'll look at, this is for an attractive potential barrier, and the one that's actually of more interest and applications is the repulsive barrier, and we'll look at that in the next segment.